A garden hose has an unobstructed opening with an inside diameter measuring 1.9 centimeters. In a previous video, using the same word problem, I solved part A, the unobstructed opening, and in this video we're going to solve part B, an obstructed opening. If you recall, here are the two scenarios, and here's water coming from a garden hose with an unobstructed opening, it's just open area. And the pipe is filled with water and you can see the water is streaming out. But what would happen if you put your thumb in the way, and thus you reduce the diameter, in turn reducing the area, and you'll notice that the water here is much faster than it is there. And yet the incoming flow, the volume flow rate going in, is the same in both cases. What's different is the velocity of the water leaving. And that can be seen using the equation of continuity. And that's what we're going to do here in part B. We're going to solve the velocity of the water here with an obstruction. Back to the original word problem, part B. Let's do a diagram. So here is the original hose without the obstruction. And we'll call this 1.1 and 0.2. And the volume flow rate going in here, Q dot, must equal the volume flow rate leaving because everything here is all the same diameter, Q dot 2. So Q dot 1 must equal Q dot 2 in this scenario. With that, the opening here is exactly the same as the opening there, and the velocity here is the same all the way through. Now looking at part B, an obstructed opening. So we're going to redraw this and reducing the opening at this end right here. That's I'm just going to draw it larger. So here it is. And there's the pipe, or the garden hose I should say, and the thumb is in the way right here. Such that now the opening is half as big as it was earlier in this scenario. And the water is leaving here, much as you can see here in this picture. And we'll call this area, or this point, 0.3, and the volume flow rate leaving is going to be Q dot 3. And what is going in is exactly the same what's coming in here, Q dot 1. Same hose, all we've done is put our thumb in the way. Another way to show this, which is a more common way to show this scenario right here, is here is the incoming hose. And it has the same diameter for a portion of the way, and then it gets reduced. Such that this portion right here is half the original diameter and the water flows out. So in here, going in, the flow rate, the volume flow rate going in, Q1, and volume flow rate coming out will be Q3. Q dot 3, the volume flow rate leaving. The difference between here and there is this is half the original diameter. Or I should say this says half the original area, opening with half as much area. Half as much area. Half the area. But continuity states that the volume flow going in, let's say we have 1 liter per second going in, 1 liter per second must come out. Whatever goes in has to equal what comes out. Therefore, Q1, if you look from here, Q1 must equal what's going out in Q3. 1 liter per second going in, 1 liter per second must come out. And looking at the continuity equation, we can just change the subscripts. Here it is here. We'll just change the subscripts to 3. And therefore Q1 is equal to Q3 is equal to area at 3 times the velocity at 3. And we can rearrange this, so just simply say what the volume going in has to equal the volume going out. So just eliminate the middle portion. The volume going in must equal the volume, the flow rate going out. So we could solve this word problem using this simple equation right here. We have all the information we need, just have to solve for V3. But I'm going to take another route. If in this case Q1 is equal to Q3, therefore, if Q.1 is equal to Q.3, looking at the right-hand side of the equations, I can make this equal to A1 V1 is equal to A3 velocity at 3. What goes in has to equal what comes out. That's what this states. Using the subscripts to denote we're talking about this area right here. Write down what is given. The volume flow rate going in has to equal, and it's written here. And I solved this in the previous video. 8 liters over 13 seconds. And we'll just write that down. 0.008 cubic meters per 13 seconds. And we'll solve this in the calculator. And that comes to 0.00615,385. And the units will be cubic meters per second. And the velocity must equal the velocity at 1. Velocity at 2 here must equal the velocity at 1. Equals the velocity here. And if this velocity then is also the same as the velocity here, and we know what this number is from the previous video. Velocity 2, we calculated to be 2.17 meters per second. So going back, remember this is that part right here. We calculated what the velocity was there, but since this is uniform, that velocity must be exactly what it is here. So that puts us at this point here. So V1, velocity at 1, must be 2.17 meters per second. Area 1 is this area, the cross-sectional area. That is equal to pi times 0.019, everything divided by 2, all squared, pi r squared. And let's put this on our calculator and arrive at a number, 0.000283529 meters squared. And the area 3 is going to be half the original area, half of this. So area 3 is half of that. It's equal to this value. Half of it divided by 2. Put in this in the calculator, the number is 0.000141764 meters squared. And we're asked to find what the velocity is exiting here. That's what we want to find. Using this equation, the volume going in must equal the volume going out in terms of cross-sectional area and velocities. Where this is Q.1, and this part here is Q.3. So what goes in must equal what comes out. Using this scenario, we have all the numbers we need. Just a matter of putting them in here. So area 1 is this term. Multiplied by the velocity going in, which we calculated in a previous video. Rounded to 3 sig figs to 2.17 meters per second. This would be meters squared, meters per second. that comes to cubic meters per second, or the volume flow rate in. Volume flow rate in is equal to A3, and A3 we said was going to be half the original diameter, which is this term, 0.000144764, multiplied by the velocity 3. If you want to put in the units, this will be the area is meters squared, and meters per second comes to cubic meters per second. So the units match on both sides. Isolating V3, which is what we want to find, dividing both sides by this term. Times 2.17, everything divided by 0.14764. That will be velocity 3. If you want to work on the units, it'll come to meters per second. I'll leave that for you to do. Put in this number now in your calculator. The answer is 4.3400 meters per second. So the velocity at 3 here is 4.3 meters per second. Using this equation, we can solve the same thing using this one, a little bit shorter. And we'll call this Q3 is equal to A3V3. Volume flow rate in has to equal the volume flow rate out, and which is equal to A3V3. We went through all of that up here. So we can reduce this to this little portion. Okay, leaving that one out. The volume flow rate in, Q1, Q rate is right here. Volume flow rate in has to equal the cross-sectional area at 3, which we said was this value. Multiplied by the velocity. Dividing both sides. (615,385) divided by this term, 0.001411764, is equal to the outgoing velocity. And doing this calculation, we get 4.340911. That little difference here and here, that's because of the rounding that was done here in velocity of 2.17. Otherwise, to two significant figures, the answer is the same. And you will note the original velocity going in, 2.17 meters per second. And we reduced the diameter, or the area here, by half. And notice that the velocity has increased by 2. 2.17 and 4.34. Multiply this times 2. So the velocity has increased. Okay, it's doubled. And you can see that here. Here is the velocity without the obstruction, and you can see the change in velocity with the obstruction. What remains constant is the volume flow rate. So if we have a certain volume flow rate here, for the sake of argument, let's say there's a 2 liters per second is flowing out, then 2 liters per second has to be flowing out here. And what's different between them is the velocities.